The title of this presentation is Display Simulation from Charge Exciton Interactions to Light Management. My name is Ruhstaller. I'm from Fluxim, as well as Zurich University of Applied Sciences in Switzerland, and I'd like to introduce my co-authors who contributed to this work. So it's a collaboration of these two institutions. We spun out from the Zurich University of Applied Sciences in 2006 as a spin-off company, and then we started out with simulation software, namely ZFOS. Initially, ZFOS contained only light emission, but later on electrical processes were added. And as you can see from this chart, we introduced measurement equipment in 2012, then a second simulation tool called LAOS in 2015, as well as angular measurement instruments, and finally stress testing hardware called LITOS and LITOS Lite. Now, why should we care about device simulations and advanced characterizations? There are lots of processes going on: charge transport, exciton generation, decay, emission, and so on. So it does help to understand efficiency, limitations, and improvements. And we can get device parameters. We can analyze degradation phenomena and do actually this kind of analysis as the device degradation is progressing. In order to study all the processes determining efficiency in an OLED, we established a 1D continuum device model that copes with charges, excitons, and photons, taking all processes into account and, for instance, considering the Purcell effect when solving the exciton continuity equation. On the left, you see the input parameters and model assumptions. On the right, the output is listed, namely measurable quantities like JVL curves and efficiency curves, but also additional insights like charge, field, and exciton profiles that basically cannot be measured directly. The only exception is the emission, which is determined by fitting angular emission spectra with the optical model. Then the best practice in solving such a model is actually to use a drift-diffusion model in solving it in one dimension. Now, in the previous example, we just took measured data from a paper and did some rough adjustment to the given data set. But in this example shown here that we published 2 years ago, we had available a set of devices that were systematically varied, and we measured them with our instrument PIOS. So this is a PIP device, simple hole-only device, where we see that the thinner the device, the more current is flowing through, and there's a tendency, also a clear tendency in the capacitance voltage curve, as well as the capacitance frequency data. And the idea here was that we wanted to adjust the model parameters to the whole set of parameters JV, CV, and CF. And this is indeed possible, and we get a very nice agreement, and from this agreement we can extract the p-doping concentration, the hole mobility in the intrinsic layer, and the confirmation of the energy barriers. The next example deals with a green-emitting phosphorescent OLED containing 3 organic layers, and in this particular prototypical device we have observed a shift of the emission zone from the anode side with increasing bias applied, and this observed split emission zone that occurs at intermediate bias is then also observed indirectly in the transient electroluminescence overshoot in the case where the emission zone is split. So we identified a correlation between a split emission zone and an occurrence of a turn-off peak when we turn off the voltage, and observed it in the transient EL. But how come there is such a correlation between emission zone and occurrence of a turn-off peak? If you look at the device in the steady state, you will notice that a typical 3-layer device has accumulation or blocking behavior for electrons at the hole transport layer and for holes at the ETL. This leads to a recombination zone that has a peak at both interfaces in the EML. When turning off the device, the potential drop is reversed, such that the carriers that were accumulated previously will then go towards the center of the device before exiting, and thus have another opportunity for giving a delayed electroluminescence. This is the origin of the peak, and such effect only occurs if there's enough accumulated electrons and holes on either side. So in other words, if there's enough emission zone intensity at either side. So the observed experimental data is shown in plot C for a range of voltages. At low voltage of 8 volts, there's no overshoot. At intermediate voltage of 11 volts, there is a strong overshoot. And at high voltage of 12 or more, that overshoot decreases again. This behavior is nicely reproduced in the simulation shown in plot D and has exactly the origin I just discussed. Once we have achieved an electro-optical model that reproduces the electrical but also optical characterization data of an OLED, we can dig deeper and analyze the efficiency behavior versus voltage. On the middle graph on the top, we plot the contributions of different processes giving rise to losses. Only the red part describes the outcoupled photons, but all the rest can be split into different processes, the pink one being triplet polaron quenching, that is actually decreasing with increasing voltage. And this is shown by the profiles that were calculated at low voltage, 5 volts. We see a large triple polaron quenching due to the overlap of excitons and holes on the right-hand side of the EML. However, if we increase the voltage to 11.5, for example, we see that the profiles shift strongly, and now we have the exciton shifted to the left. So this is actually the emission zone shift I just talked about in the previous example. But now the exciton maximum is no longer where the holes were accumulating on the right-hand side. So effectively, we have decreased triple polaron quenching. But now at high voltage, the exciton density is much higher, on the order of 10 to the 17 compared to 10 to the 15 at low voltage for 5 volts, such that now at high voltage we get an increased triplet annihilation, shown as a turquoise bright blue cyan contribution that is increasing at higher voltage. So finally, we can draw the schematic behavior of what's going on. At low voltage, we have emission zone on the right-hand side of the emitter layer. At intermediate voltage, we have a split emission zone that was already proven by the occurrence of the transient EL overshoot in the previous slide. And at very high voltage, we have a roll-off that is actually due to triplet annihilation. Whereas in the previous example of a phosphorescent OLED, we only modeled one exciton, namely triplets representing the ERP molecules. Now we look at a 5-layer TADF OLED containing an emitter layer with a co-host and a fluorescent dopant DAISY GDB. The TADF mechanism is realized in the co-host. Their triplets experience reverse intersystem crossing due to thermal activation, and there's a resonant energy transfer to the dopant. So we model 3 types of excitons in total. For this state-of-the-art OLED, we performed a detailed analysis, again using an optically tuned and a detuned OLED. The latter detuned OLED allows us to determine the emission zone of the OLED, and to establish the material parameters for the electrical device model that is then also used to describe the tuned, more efficient OLED. As you can see, the current efficiency versus voltage data is nicely reproduced, and we can identify that the efficiency peak near 2 volts is observed due to triplet harvesting thanks to thermal activation. Now the key question is which material parameters should be optimized to avoid the efficiency roll-off. The graph in the middle on the bottom shows a variation of 5 parameters. The roll-off can indeed be reduced if either the intersystem crossing rate is increased and the TTA rate is decreased. To give you an idea of the agreement between the measured outcoupled spectra and the simulations from the electro-optical model, here's the data for the tuned thin and the detuned thick OLED. The optically determined emission zone in blue dots shown on the right-hand side is well reproduced by the electro-optical model given in lines. Again, we observe a split emission zone. Next, we look at the parameter extraction methodology for another type of TADF OLED. In this case, it's the sky blue emitter material from Sinora. A systematic OLED stack variation was performed by varying the HDL and EGL thickness. And lots of data sets were acquired by taking DC, AC, and transient measurement data. This provides a rich data set suitable for parameter extraction by globally fitting a drift-diffusion model to the data. We establish a fitting procedure that is sketched below, but in view of time, I refer to the recently published paper. We increase the complexity of the physical model step by step, motivated by distinct features in the analyzed curves. The final fit simultaneously matches with multiple OLEDs and multiple experiments, as you can see in the graphs where the thin lines are the simulation. Let's have a look at some more interesting stuff which we can analyze thanks to the simulation. On the left, we show the recombination profile as a function of applied voltage. The recombination, and thus the emission, is predominantly occurring at the EML-ETL interface and gets narrower with increasing voltage. The same trend was obtained when doing emission zone fitting on detuned devices, which is completely independent characterization techniques, which is based on the angular instrument phalos and ZFOS. And finally, also in literature, there's a very similar stack that was published, and the authors also reported a rather narrow emission zone at the EML-ETL interface, which is again in agreement with our results. Such a narrow emission zone could be detrimental for device stability. It could therefore be beneficial to adapt the electron transport in the EML using a co-host approach. In the second part of this study, we analyzed the degradation behavior of the TADF OLED. The OLED was stressed at a current density of 15 milliamps per square centimeter, while the voltage and luminance was recorded, as shown on this graph. At specific points in time, a full pious measurement routine was performed, including JVL, CV, CF, transient EL, darkened injection CLIF. Together with the device simulation, this comprehensive dataset allowed us to investigate different potential degradation pathways. Here we show the results of a few data sets during the OLED degradation as it progresses from initial to 15 hours after the initial measurements. Some of the characterizations techniques do show no much difference, namely capacitance frequency graph. Other data sets like the JV show systematic variation. And again, it was crucial to consider impedance transient data besides the more traditional steady-state results. Now, in order to get a qualitative understanding of which processes could be going on and be responsible for the degradation, that is observed in these systematic measurements, we can vary certain parameters. For example, we can look at the change in hole transport variation. First, we look at the hole injection barrier parameter. Indeed, an increase in hole injection barrier causes the same changes in the transient EL rise and C-lift and also in the impedance data as seen in the experiment. Therefore, this parameter could be responsible for the charge transport modifications during stressing. The same applies to the NPB hole mobility. Also here the changes in simulation are qualitatively similar with the experiments. However, a change in the TCTA or in the EML mobility, hole mobility, can be excluded as those would result in a different transient EL or C-lift change, respectively. Similarly, we can investigate several hypotheses for degradation, but I don't have time to go in much detail here. I just would like to stress that the measured current efficiency versus stressing time is actually dropping with increasing stressing time. And one possible explanation for this could be the formation of non-radiative recombination centers inside the EML. We know that such trap states are predominantly formed at locations with high exciton concentrations. This has led us to assume that maybe at those locations we could introduce trap states in the simulation. So we just use the same emission profile as trap density profile. When we compare the current efficiency trends upon degradation on the left with a trend in simulation upon increasing trap density on the right, we see a good qualitative agreement. Therefore, we conclude that the electron traps are formed in the EML at locations of high exciton densities and that those are responsible for the decrease in efficiency. Now I would like to introduce a new hybrid 3D master equation 1D Drift-diffusion OLED model. And to motivate that, I would like to summarize the two main approaches for OLED modeling electrically. So there's one approach called continuous deterministic drift diffusion approach. That's basically what was used in this presentation so far. It is a very efficient calculation method. It takes seconds and minutes only. However, it may lack physical accuracy, especially if it comes to excitonics. Exciton interactions and migration, that's a long range involving long range processes. And then alternatively, there are atomistic approaches like kinetic Monte Carlo or master equation. They allow to implement fancy, sophisticated physical models in 3 dimension. However, this is usually a very computationally demanding approach, requiring hours, if not days, of computation time. Now, definitely in the community, there is a need for fast, reliable, and precise algorithms. And what we are trying to do now is to actually combine the best of both worlds to offer high physical accuracy at still moderate computational cost. And this is now the baby born hybrid 3D master equation 1D Drift-diffusion OLED model. And we have recently published this model approach in this publication listed here. Now, what do we mean with the hybrid 3D master equation 1D Drift-diffusion model? We'd like to take advantage of the large area thin film device configuration in which the applied electric field basically just points in one direction. 1D Drift-diffusion model thus solves the Poisson equation for the electric potential alongside the electron and hole current continuity equations, as shown in the upper green box here. The 1D Drift-diffusion model features advanced models ingredients such as trapping, layer polarity, sophisticated mobility models, and charge hopping at interfaces, and even mobile ions that are present in perovskite devices. The excitonic part, however, is solved with a
discrete 3D master equation modeling approach. A singlet and triplet occupation number chi of each molecule takes into account radiative decay, intersystem crossing, polar unquenching, exciton annihilation. These are processes that actually have a long-range character. So the molecules, not only near neighbors, are interacting, but further distant, for instance, from the middle layer to the neighboring transport layer. Now, in order to check the sanity of our hybrid model, we're going to compare our results to a reference publication where a full 3D master equation model was used and implemented also for the charge transport. In this example, we're looking at a phosphorescent ERPI-based 3-layer OLEDs, and the plot on the right shows the distribution of triplet excitons. So the central layer is the emissive layer, and you see that the hybrid model actually gives very similar results as the full 3D master equation approach, but the hybrid model is giving these results at a much reduced computational cost, and nevertheless the complex multi-layer host-guest system can still be modeled with ease. After having confidence in this hybrid model, we're going to apply it to a OLED simulation, in this case also a phosphorescent OLED, a red-emitting phosphorescent OLED. And here we want to understand the efficiency roll-off that is maybe linked to exciton polar unquenching, TPQ. So the literature data that we looked at was published 2015 by the Britting Group, and they have applied a bias to get an electroluminescence signal, but in addition applied also a laser pulse, and they analyzed the light pulse decay of this PL signal, and at low applied bias there is moderately slow decay, but if you increase the current you will have more quenching going on between triplets and polarons, and then the rate of decay is increased. In our hybrid model we get similar results. First of all, the DC distribution of recombination. The higher the applied bias, the more excitons are generated here due to recombination. And the PL transients that are calculated actually do show the same effects as in the experiments. At low bias we have a slow decay, but as soon as this additional quenching mechanism kicks in at higher bias, then the PL decay transient will also decay much faster. So this is a nice example that this works out fine, and you can play around with material properties to study the influence of them. So the presented hybrid model, consisting of 1D Drift-diffusion for carriers and 3D master equation for excitonics, enables us to benefit from the best of both worlds. On the one hand, the physically sound modeling of excitonics effects with long-range interactions and transport in 3D, as well as fast and efficient simulation of charge carriers and electric fields. The implementation in our software ZFOS version 5.2 will thus allow to make seamless simulations from charge to exciton to photon processes, as we can attach the optical model to that calculation to get also the light outcoupling effects. In conclusion, we hope to have shown you that the 1D Drift-diffusion model itself is already a powerful tool which allows us to study a lot of physical effects, like new interface models for hopping, polar layers, exciton quenching, charge trapping, and these allow the study of the simulation of tandem OLEDs, TADF OLEDs, and so forth. We also introduced a new hybrid model combining 3D master equation and 1D Drift-diffusion, combining the best of two worlds. Moreover, in the beginning of the talk, we've introduced some examples of fitting the model to experimental data, which is also an art in itself, and it's very important to monitor what's going on in the device. So one example of a study was given where the OLED degradation could be explained by a reduced supply of hole carriers, as well as the formation of non-radiative recombination centers, namely electron traps, at the location of high exciton densities. These results shown today were achieved with the simulations of Drift-diffusion and the measurement instrument PIOS. Well, thank you for listening, and I would also like to thank the people that carried out this work, especially Simon Cedar, who developed the initial version of our 3D master equation model. And I thank the funding agencies that supported some projects in Europe, and also the samples that were provided for some of these studies, especially the TADF OLEDs that were provided by Sonora and Technical University in Dresden.